Select the correct equations that show that a machine that has an input of 100 joules and an output of 70 joules is 70% efficient. In general, efficiency is what you want over what you pay. So below that you see that funny looking letter. It looks like a weird N. It's actually Greek letter eta, E-T-A, and it symbolizes efficiency. Because efficiency is defined as what you want over what you pay, in this case, what do I want? I want output energy. How do I pay for it? Input energy. Even more specifically, I want a machine that does 70 joules of work, that provides 70 joules of energy output, and I have to feed it 100 joules of input energy in some form to get that output. How much work is required to lift a 280 kilogram appliance to the second story level of a house 6 meters above street level? Okay, well, I know work is force times distance, or I can shorten that to W equals F times D. In this case, the force is the gravitational force, which we know as weight, and we know that weight, W equals mg. So as far as work is concerned, work is m times g times d. So when I plug in the values for m and for g and for d, I'm going to get the right answer, but I also want to make sure to do the dimensional analysis. So from a units point of view, what do you get when you take kilogram, multiply it by meter per second squared, and multiply again by meters? You get kilograms times meters per second squared times meters, which is a Newton times a meter, which is a joule. Next problem. How much work is done when you push a crate horizontally with 90 newtons across a 13-meter factory floor? Okay, well, once again, number one, work is force times distance, and in this case, the force applied to this crate is 90 newtons, and it's acting on the crate as the crate moves through a distance of 13 meters. So 90 times 13 is the numerical part. But from a dimensional point of view, I have newtons times meters, which is also known as the joule. Okay, part B says if the force of friction on the crate is a steady 70 newtons, find the kinetic energy gained by the crate. Here's my drawing. This is the 90 Newton force that I'm applying to the crate. This is what I dealt with in part A. This is the distance through which that crate moves, 13 meters. Now, however, I have this friction force. Friction always opposes velocity. So if the box is moving to the right, this friction force is going to be acting to the left. It's always going to try to fight velocity, the direction of velocity. Notice I'm using lowercase f, which stands for friction, and that subscript k means kinetic friction. Kinetic friction is the friction that arises when one object is sliding over another object. Okay, this is going to be a job for the work kinetic energy theorem. This is the equation. The net amount of work done on an object is equal to that object's change in kinetic energy. So then I guess I'm wondering, what is the net amount of work done on this object? The net amount of work done in this case is going to equal the net force acting on this object, F underscore net, times the distance through which that object moves. So what's the net force? In this case, the net force is going to be that 90 Newton force, which is going to the right, so that is positive, minus the 70 Newton friction force, which is going to the left, so that gets a negative. My net force, therefore, is 20 newtons going to the right. So once again, my net work is going to be my net force, which is 20 newtons going to the right, times the distance through which this object moves, which is 13 meters. 20 times 13 is easy enough. My units are newtons times meters. So the net work done is going to be some number of joules, because a Newton meter is a joule. And once again, the net work done on an object is equal to the change in that object's kinetic energy. Because the net work done is positive, 20 newtons times 13 meters is a positive times a positive, that means the change in kinetic energy for this object is also positive, which means there's a gain. The object gains that amount of kinetic energy. It speeds up. Part C is asking, find the missing energy. Well, I know the missing energy is due to friction. Friction generates heat. Just rub your hands together on a cold day and you know that. Friction generates heat, and it's that heat energy that is said to be stolen or lost by the system. So even more specifically, we need to find the work done by that friction force, because that friction force does some amount of work, and that work is actually generating heat. I know how to calculate work. Work is generically force times distance, and here very specifically it's going to be that kinetic friction force, that's the F, times the distance, which is still 13 meters. So number 3, here's the amount of energy missing or lost to the system. It's going to be my kinetic friction force, which is given as 70 newtons, times the distance through which this force is acting on the object, which is 13 meters. I should note that the friction force is acting to the left and the box is moving to the right. So once again, if the box is moving to the right and the force is acting to the left, that would be negative energy. So you're going to get some number, and technically that number should be a negative number if we really wanted to be accurate. The units are once again newtons times meters. So technically you're going to get some negative number times joules, but in this case they don't want you to record the negative. They just want you to state the amount of work done by friction, which is the same as the amount of heat done by friction, and it's that heat energy which is the missing energy. Next problem. Belly flop Bernie dives from atop a tall flagpole into a swimming pool below. His potential energy at the top is 15,000 joules relative to the surface of the pool. So here's my drawing. This red dot represents the diver, and I'm going to say right now that PE, which stands for potential energy, equals 15,000 joules. That's the given. So the question asks, what is his kinetic energy when his potential energy reduces to 1,000 joules? So as Bernie falls towards the swimming pool, at some point his potential energy, his gravitational potential energy, is going to diminish to 1,000 joules. This is a job for the conservation of mechanical energy. Remember, mechanical energy, M for mechanical, E for energy, is the sum of kinetic energy and potential energy. Conservation of mechanical energy means it doesn't change. So I'm going to say delta mechanical energy, which means the final mechanical energy minus the initial mechanical energy equals 0, which means, number 3, whatever mechanical energy you end up with has to be the same as the mechanical energy you started off with. The diver's initial mechanical energy was purely gravitational potential energy, and I say that because the diver starts from rest, which means no kinetic energy. So the diver's initial kinetic energy is, as stated, 15,000 joules, and all of that is potential energy, gravitational potential energy, because, once again, there's no kinetic energy at the top of the flagpole. The final mechanical energy, MEF, equals the kinetic energy plus the potential energy at that final position. So kinetic energy is K, and I don't know what that is. I'm trying to figure it out. But the potential energy is 1,000 joules, as stated in the question. So this is my mechanical energy initially, 15,000 joules. This is my mechanical energy at the final state. Number 6 then means that 15,000 joules of mechanical energy that the diver started off with has to equal some amount of kinetic energy plus 1,000 joules. So you can solve for the amount of kinetic energy that the diver has when all of that potential energy, or most of that potential energy, got converted into kinetic energy. Nellie Newton applies a force of 50 newtons to the end of a lever which is moved a certain distance. If the other end of the lever moves 1/3 as far, find the force it can exert. A lever is a simple machine, and we like simple machines because they give us a mechanical advantage. Mechanical advantage means that you're able to apply an input force and the output force is multiplied. It's a force multiplier. So here's how you could write it. Mechanical advantage is the ratio or the fraction of output force to input force. So it's almost magical. I can apply a certain input force and the lever will magnify it or amplify it to produce a greater output force. It's almost as if you're getting something for nothing. The catch is the amount of work you do is going to be the same. So the work that is done at that output is going to be the same as the work you do at the input. That's basically conservation of energy. So the output work could be written as output force times that output distance, and that has to equal your input force times the input distance or the distance through which you apply that force. This is the output work that is performed. This is the input work that you yourself invest. They have to be equal. The other side of the lever will move through a distance of 1/3 of a meter. How do I know that? Because the problem says I apply my force through a distance of 1 meter and the other side of the lever moves 1/3 as much. So if this moves through a distance of 1 meter, this moves through a distance of 1/3 of a meter. I'm going to go back here to step 5 and basically solve. My output force is going to equal my input force times the distance through which that input force moves divided by the output distance. So with numbers, my output force is going to be the input force, which is 50 newtons, times input distance, which is 1 meter, divided by the output distance, which is 1/3 of a meter. And I know how to solve that. My output force is therefore 150 newtons. So the moral of the story is I apply a 50 newton input force and I magically get 150 newton output force. But here's the catch. I had to apply that input force through a distance of 1 meter, and at the output end, the lever only moved 1/3 of a meter. But that's okay. Maybe I'm okay with that smaller distance because my whole goal is to minimize the force that I have to apply. So in this case, the mechanical advantage is going to be defined as the output force over the input force. So my output force was 150 newtons and my input force was 50 newtons. So this mechanical advantage is 3. The amount of work done is the same, but I do have a mechanical advantage as far as force. Next problem. Consider an ideal pulley system. If you pull one end of the rope 1 meter downward with a 60 newton force, find the height you can lift a 240 newton load. Okay, a pulley is another simple machine like the lever. We like simple machines because they give us a mechanical advantage, MA. Remember, mechanical advantage is defined as output force divided by input force. Also remember that just because a simple machine can multiply your input force, the input work that you do has to equal the output work that is done to an object. That's what I'm saying here in number 3. The input work equals your input force times the distance through which your input force acts, and that has to equal the output force that is generated by the simple machine, in this case the pulley, times the output distance through which that output force acts. So I go from step 3 to step 4 where I'm just isolating the output distance, and you can see the rest is pretty simple math. Next problem. In the hydraulic machine shown below, when the small piston is pushed down 10 centimeters, the large piston is raised 1 centimeter. If the small piston is pushed down with a force of 150 newtons, what is the most weight that the large piston can support? Okay, here's another simple machine, which means we think of mechanical advantage. Mechanical advantage is the ratio of output force to input force. Remember, though, that these simple machines can multiply your input force, but they can't multiply work. The work I do at the input is the same as the work done at the output. My input work is my input force that I apply times the distance through which my input force is applied. The output work is the output force that's produced times the output distance through which that output force acts. In this case, the output force has to match the weight that is sitting on that output piston. So in step number 6, I'm isolating the output force in step 4, and when I plug in numbers, I get a 1500 Newton result. When I apply an input force of 150 newtons, I can miraculously support an output force of 1500 newtons. Remember, though, the price I pay, I have to push my input force through a distance of 10 centimeters to get that output force, or that weight, to move only 1 centimeter. But again, maybe that's a price I'm willing to pay. Emily drops a banana of mass M over the edge of a bridge of height h, and it falls to the river below. From the initial potential energy of the banana converting to kinetic energy, find the speed of the banana just before hitting the water. Okay, this is a job for the conservation of mechanical energy, ME, mechanical energy. Mechanical energy is the sum of potential energy and kinetic energy. Because mechanical energy is conserved, we can write down delta ME equals 0. And we know by now what delta means. Delta means final minus initial. So in step 4, the change in mechanical energy is the final mechanical energy minus the initial mechanical energy, and it has to equal 0. That's what it means to be conserved. So in step 5, I can say whatever mechanical energy that banana starts out with, it has to equal the mechanical energy of the banana by the time it hits the river below. Okay, the banana's initial mechanical energy is the sum of its initial potential energy and its initial kinetic energy. The initial potential energy is mgh, and I'm going to use the subscript I for initial height. And my initial kinetic energy is 0 because it's starting from rest. Starting from rest means no velocity, means no kinetic energy. So the banana's total amount of initial mechanical energy is just simply mgh subscript I. My final mechanical energy is the final potential energy plus the final kinetic energy. At the very bottom, the banana's height, hf, equals 0. The banana's kinetic energy is k subscript f. So the banana's final mechanical energy is just its final kinetic energy because it has no gravitational potential energy. Kinetic energy is 1/2 mv squared, and I'm just using that v subscript f to specify final velocity of that banana at the point it hits the river. So in step 9, once again, the banana's initial mechanical energy has to equal the banana's final mechanical energy. The initial mechanical energy is mgh subscript I, and that has to equal the final kinetic energy, which is 1/2 mvf squared. So my job now is to isolate the final velocity of that banana, and you can see that's what I'm doing here in step 11 and step 12. Next problem. A ball is released from rest at the left of the metal track shown below. Assume it has only enough friction to roll, but not to lessen its speed. Part A, rank the momentum from greatest to least at each point. Momentum is something we technically haven't talked about yet, but I can introduce it here. Momentum, which usually is represented by the letter P for whatever reason, is mass times velocity. Momentum is mass times velocity. So if we need to find out what the greatest momentum is, we have to ask ourselves, where do we have the greatest velocity? So as far as the figure you see at the left, right here, this is 0 velocity because it's starting from rest, and then here this is greatest velocity. So I know C is probably the greatest momentum because the object has the greatest velocity. At B and D, the speed is the same, and this is a momentum, but it's also a conservation of mechanical energy problem because right here on the at part A, I have lots of gravitational potential energy. And here at C, all of that potential energy got converted into kinetic energy here. Lots of kinetic energy here. So if I'm going to rank them, I would say the greatest would be at C, and the second greatest would be at B and D, and the least would be at A because I'm starting from rest. Part B, rank the kinetic energy from greatest to least. I think I covered that. At Part A, I have no kinetic energy because I have pure potential energy. At Part C, I have the greatest amount of kinetic energy because I have the greatest velocity, because all of this potential energy at A got converted to all of this kinetic energy at C, and then B and D would be once again in the middle, tied for the middle, because they have the same velocities. For the next problem, 759, it wants you to rank the speed, kinetic energy, and potential energy. Well, you can see, obviously, my potential energy at A is the greatest because it's just a function of mgh. PE equals mgh. And then I guess by that same thinking, you could say the potential energy at D is the least because my height at D is the smallest compared to A, B, C, or E. And I guess you could also say at D, my kinetic energy is greatest because kinetic energy equals 1/2 mv squared. And all of this potential energy at A got converted into that kinetic energy at D. Maybe not all of it, but you can see a lot of it. Whereas at A, all of this potential energy at A, a lot of it got converted into kinetic energy at B, but not as much as was converted to the potential energy at D. So that's, I think, one way to look at it. This is just like that energy skate park exercise. It's also conservation of mechanical energy, which is always conserved. So you could say whatever the total mechanical energy is at A, that's got to equal the total mechanical energy at D. And that's true between any 2 points. The mechanical energy at B has to equal the mechanical energy at E, for example. Mechanical energy is the same anywhere between any 2 points. My potential energy at B is greater than my potential energy at D. That means my kinetic energy at D has to be greater than my kinetic energy at B. It's that simple. Next problem, 7.60. You need to rank the scales for each of these 3 pulley situations. A pulley is another simple machine, so let's take a look at what's happening in A. This person is holding this block stationary. This block has a weight of force. Weight is the force acting on the block from the earth, which means this tension force has to be exactly the same value except going upward. Tension is a force transmitted by a string, a cable, a wire, a rope, etc. This tension force here that I'm indicating, this is the tension force that is being exerted by this person via the scale. So it's this tension force here that appears as the scale reading. This tension force has to be the same as this tension force because it's the same string, and the tension force is distributed evenly through a piece of string. So I know that the tension force acting on that block is the same as the block's weight, and it's that tension force that also appears as the scale reading. In B, I have the same block, which means I have the same downward acting force exerted by the earth on the block. This is a gravitational force acting downward, which means these 2 upward forces have to combine to perfectly offset that downward weight force. The pulley is basically an intermediary that does provide a mechanical advantage. These 2 tension forces combine to perfectly offset this weight force. And whatever the tension force is here in this rope or in this rope has to be the same as the tension in this rope, and this rope is attached to my scale. So this is my scale reading right here, this tension force. So if I add everything up, or if I make sense of everything here, this tension force and this tension force have to equal the weight. So therefore, whatever the tension force is, it's the same as the weight divided by 2. And once again, that is my scale reading. It's kind of tricky at first, but hopefully it makes sense. These two tension forces right here combine to offset this weight force right here. In part C, same thing. I have a downward force acting on the block. This is called weight, or the gravitational force. I have, again, two tension forces acting up. So this tension force along with this tension force, these two forces have to combine to perfectly equal the weight force. Again, mechanical advantage. I have this tension force plus this tension force equals the weight. So this is the same result. My scale reading here in part C is going to be the same as it is in part B. Next problem, 760. This is a typical driver's license question. A car moving at 50 kilometers per hour skids 15 meters with locked brakes. So part A, how far will the car skid with locked brakes at 150 kilometers per hour? So I'm going to start here. This is the work kinetic energy theorem. This is one of the big equations in your green sheets. The net amount of work done on this car equals the car's changing kinetic energy. I know that work is force times distance, and I know that delta K means final kinetic energy minus initial kinetic energy. And I know my final kinetic energy is 0 because it skids to a stop. So in number 3, there's my F. I don't know what it is, so I'm just going to leave it as F. But I do know D. D is 15 meters. And in 15, because it's given as 15 meters, in 15 meters, my kinetic energy goes from some big number to 0. So I have negative 1/2 mv squared, because I remember that kinetic energy is 1/2 mv squared, and that's what I'm looking at here. This is 1/2, this is m, this is v squared. And again, this negative 1/2 right here, right there, came from the fact that I had this negative here. All right, so step number 4, if I want to get F all by itself, I have F, which is the force that your brakes apply to bring your car to a stop or to slow it down. From number 3, I can isolate F, and I get negative 1/2 m. I don't know what the mass is. I'm just going to leave it as m. Times v squared, and then 15 appears in the numerator. Step 5, at a higher speed, now I'm going much faster. It's still the same work kinetic energy theorem. Work is still force times distance. Delta K is still final kinetic energy minus initial kinetic energy, and my final kinetic energy is once again 0 because I'm skidding to a stop here as well. Number 8, work, which is force times distance, is negative. That negative sign can't be forgotten about. And here's my initial kinetic energy, 1/2 m. I don't know what the mass is, so I'm just going to leave it as m, times my new velocity. This is my 150 kilometers per hour, which is greater than that 50 kilometers per hour number that I had before. So I'm going to do the same thing in step 9. I'm going to get force all by itself, and when I do that, you can see I basically just divide both sides by d. So this is what I have. This is my expression for force, but now remember, this is like aha. I also remember that this is F as well. So I have two equations for F. This equation here came from step number 4. And F is the same. So this force here, whatever the force is to begin with, this is my braking force. So that braking force is always the same. That braking force is the same as this braking force. So now I have this equation that I'm circling in green, and I can solve for D. This is what I'm going to do in step 10. I can cancel. You can see a lot of stuff cancels right away. On the left side, I have minus can cancel with minus. 1/2 can cancel with 1/2. M can cancel with M, which is a good thing because I didn't know the mass anyway. And then I'm left with this in step 10. I'm left with 150 squared divided by D equals 50 squared. This remains 50 squared over 15. That's the 15 there. And then this is my final answer for D. So this is what your calculator will spit out for D. Next problem, 757. The mass and the speed of the three vehicles A, B, and C are shown. Rank them from greatest to least as far as their momentum is concerned. Once again, momentum is equal to mass times velocity. Momentum, we're technically not covering momentum yet, but just to get through this question, I will sort of preview it for you. Momentum is mass times velocity, or M for mass times V for velocity. So for A, the mass of automobile A is 800 kilograms. The velocity of A is 1 meter per second. For B, the mass of automobile B is 1,000 kilograms, and it's moving at a velocity of 2 meters per second. And C, momentum, P is used for momentum for a mysterious reason. The mass of automobile C is 90, and the velocity is 8. So that's going to be pretty easy to rank their momentums from greatest to least. Okay, the next question wants you, or the next part of this question wants you to rank these situations in terms of their kinetic energy. And we know that kinetic energy is equal to 1/2 mv squared. So for automobile A, 1/2 times 800, which is the mass, times the object's velocity, 1 meter per second squared, equals 400 kilogram meters squared per second squared, which is the same thing as 400 kilogram times meter per second squared times meter. And I know that that is the same as 400 Newton meters, which is 400 joules. For part B, automobile B, I should say, 1/2 mv squared is the same as what you see here. And this is 1/2 mv squared for automobile C. So go ahead and get the numerical values for part B, or I should say get the numerical value for automobile B and automobile C. You have it here, at least with my numbers for automobile A, and rank them accordingly. Part C wants you to rank these situations in terms of the work needed to bring them up to the speeds shown. Once again, this is the work kinetic energy theorem equation. The net amount of work done on an object is equal to that object's change in kinetic energy. So the work done for automobile A to bring it from 0 to its shown speed is going to equal the change in automobile A's kinetic energy. Delta K is always final minus initial, and the initial is 0 because it's starting from rest. So here's the work needed to bring automobile A up from 0 velocity to its shown velocity. It's just going to be whatever the kinetic energy is, because there's no initial kinetic energy. Kinetic energy is 1/2 mv squared, and I'm using subscripts, which are very helpful. For A, 1/2 times the mass of A times the velocity of A equals 400 joules. So do the same approach for B and C. You're going to do the same approach for B, and you're going to get this number, whatever it equals, whatever your calculator says that equals, and you'll do the same thing for C. C will be, the work done is going to be equal to 1/2 times the mass of C times the velocity of C squared, and then you're just going to rank them according to their work values. This is the work done on automobile C, this is the work done on automobile B, and this is the work done on automobile A. Next problem, 7.53. How many watts of power do you expend when you exert a force of 35 newtons that moves a crate 7 meters in 3 seconds? This is a job for power. Power, P, is defined as the amount of work done per time. So time is a critical element here. So I know what work is. Work is force times distance, and my numerator is T for time, because power is work divided by time, the rate of doing work, even more specifically, the time rate of doing work. My force applied to this crate is 35 newtons, it's moving, this force is acting through a distance of 7 meters over a time period of 3 seconds. So numerically, this is my power, 81.7, and you can see my units. I have Newton times a meter per second, and I know that a Newton times a meter is a joule. So I have a joule per second, and a joule per second is defined as a watt. 1 watt equals 1 joule per second. So I have 81.7 watts of power used to accelerate this crate by applying a force of 35 newtons on it over a distance of 7 meters over a time interval of 3 seconds. The power that I invested to make this happen is 81.7 watts. Next problem, 744. Select the correct equations that show that a 900,000 joule change in kinetic energy occurs for an airplane that is moved 300 meters in a takeoff by a sustained force of 3,000 newtons. So I have work. Here's the amount of work that's done on this airplane. Work is force times distance through which that force acts. So my force is 300 newtons times 300 meters. That is the distance through which my force is acting. Numerically, I have 900,000 newton meters, which is the same as 900,000 joules. So that's my answer. I have 900,000 joules of work was done on this object, on this airplane, and that is in fact the change in kinetic energy, because once again the net amount of work done on an object is equal to that object's change in kinetic energy. Next question, 738. Select the correct equations that show that 1400 watts of power is expended when a 700 newton crate is lifted 4 meters above the floor in 2 seconds. So again, power is the rate of doing work. The rate of doing work can be written as work per time, work over time. Work is force times distance through which that force acts divided by time. Now here's something we should talk about. The force I'm applying has to equal that 700 newton weight of the crate. So this crate has to be lifted, which means I have to apply a 700 newton force to counteract that 700 newton weight of that crate. And you could argue, and you'd be right, that I have to provide maybe a little bit more than that 700 newtons just to get it moving upward, but we're looking just at that break-even point. 700 newtons of force is needed from me to counteract the force of gravity, which is the weight. I'm applying that force through a distance of 4 meters, and I'm taking 2 seconds to do this work. So this is what I have. 1400 newton meters per second is the same as 1400 joules per second, which is the same as 1400 watts. Next problem, 741. Select the correct equations that show that the kinetic energy of a 1.0 kilogram hamster running at 7 meters per second is 24.5 joules. Kinetic energy is equal to 1/2 mv squared. So here's my 1/2. Here's the mass of my hamster, 1 kilogram. My hamster is running at 7 meters per second, and I square that. So numerically, that's 24.5. And then the unit game again, the dimensional analysis, kilograms times meters squared is the same as a kilogram times a meter per second squared times a meter, and a kilogram meter per second squared is a newton, and then there's my meter, and that's how I get joules. I think they're using W instead of K because maybe they're thinking of the fact that work, W, equals change in kinetic energy equals final kinetic energy minus initial kinetic energy. And if the initial kinetic energy is 0, then once again, you know that work is just going to equal the kinetic energy. Next problem, 735. Work is force times distance. So here I have an 8 Newton force acting through a distance of 1.1 meters. 8 times 1.1 is 8.8. From a unit point of view, I have newtons times a meters, and a newton times a meter is a joule. 1 joule equals 1 Newton meter. Next problem, 756. A 2.5 gram penny is dropped from the top of the Empire State Building, falling 381 meters to the sidewalk below. If the penny experiences almost no air resistance as it falls, find its kinetic energy just before striking the sidewalk. Okay, here's my visual. My penny starts here, 381 meters above the sidewalk, which is right here. I'm going to convert from 2.5 grams to kilograms by multiplying with my conversion factor. There's 1 kilogram for every 1,000 grams. So this is my way of just multiplying by the number 1. 2.5 kilograms, 2.5 grams is the same as 0.0025 kilograms. I'm remembering that little yellow ball demonstration where I dropped that yellow ball as a way to state that the network acting on an object equals the change in kinetic energy. And you've had that many times before. That's the Work kinetic energy theorem. And that little yellow ball demonstration gave us this addition. So what I'm highlighting here, this is a very big cornerstone of energy analysis. And then from there, I move on to step number 2. Final kinetic energy minus initial kinetic energy is delta K. My initial kinetic energy is 0 because it's starting from rest. It's just being held up there at the top of the Empire State Building. Here's that negative sign, and here's change in potential energy. Change in potential energy is my final potential energy minus my initial potential energy. My final potential energy is 0 because right here, right at the very bottom where it hits the sidewalk, there is no potential energy because at that location, H equals 0. So I'm left with final kinetic energy, which is what I'm looking for, equals my initial potential energy. This is conservation of energy, you could say as well. My initial potential energy is mgh. My mass is 0.0025 kilograms. G is 9.8, and H is 381. So this is my final answer. Just as a quick aside, you actually could have used change in mechanical energy equals 0, which is, this is the conservation of mechanical energy, which means delta ME is mechanical energy final minus mechanical energy initial equals 0, which is how I can say that my initial mechanical energy equals my final mechanical energy. My initial mechanical energy is my initial kinetic energy plus my initial potential energy. My final mechanical energy is my final kinetic energy plus my final potential energy. My initial kinetic energy was 0 because it was dropped from rest. My final potential energy is 0 because H equals 0. And if H equals 0, then mgh equals 0. So I could once again say that my initial potential energy equals my final kinetic energy, which is exactly what I was saying right here in step 3. So just another way to get to the same conclusion.